So today we're going to talk about delivering H- to carbonyl compounds. H- is hydrogen with two lone pairs, negative formal charge. We call that hydride. Now the problem with hydride is, first of all, it's not a good leaving group. It's not a good, problem with hydride is that it comes in the form of sodium hydride, and that's not very soluble in organic solvent. You may have used sodium hydride in 351 as a base. It's a decent base, but if you put it in an organic inorganic solvent, it sort of sits as this insoluble chunk at the bottom of the flask. Organic molecules can come to the surface and react with the hydride, but typically that surface is so big that the hydride just reacts as a base instead of as a nucleophile. So we're going to need some special reagents to actually deliver the hydride to the carbonyl compound. So we're never going to see hydride on its own floating around and attacking some kind of carbonyl compound. That just isn't reasonable. So we have to use some other kinds of reagents to deliver hydride. One of these is called lithium aluminum hydride. Okay, and some chemists get lazy and decide to call it whatever. Lithium you can think of as the counter ion. It does play a role, but we're going to mostly ignore that. Aluminum is bonded to 4 different hydrogens, and aluminum, if you'll notice, is from the same column of the periodic table as boron. So like boron, when bonded to 4 things and surrounded by 8 electrons, aluminum has a negative formal charge. Okay, so right away you're seeing that this reagent has a portion of it that has an excess of negative charge. Now, aluminum is actually more let me say that backwards because the way I started to say it was wrong. Aluminum is actually less electronegative than hydrogen. Remember, formal charge is just about counting electrons. It doesn't necessarily tell you where the electron-rich portions of the molecule are. Because hydrogen's more electronegative than aluminum, actually, most of that negative charge is held out on the hydrogens, which means that the electron-rich portion of the molecule is the hydrogens and not the aluminum. Okay, so this aluminum hydride is a source for electron-rich hydrogen. All right, so how does this work? So let's just take an aldehyde to begin with, and let's react lithium aluminum hydride with it. The way I'm going to draw this is just to have a hydrogen bound to aluminum with a negative formal charge on aluminum. I'm only going to draw one of these aluminum hydrogen bonds because we're only going to need one. We're going to show aluminum handing off H and these 2 electrons directly to the carbonyl carbon. Okay, so there's going to be some things about that maybe make you uncomfortable. The one that shouldn't is the idea of an arrow pointing at the carbonyl carbon. We talked last time about how carbonyls are electrophilic at the carbonyl carbon. The LUMO of that molecule is the pi star. Most of it is on the carbonyl carbon. That's the electron poor part of the molecule. So having a nucleophile attack here is fine, and we would expect the pi bond to break and the electrons to move out on the oxygen. That should be familiar to you now. The thing that might make you feel a little bit weird is how on earth does this process happen? Why am I starting an arrow at a bond between 2 atoms, and then how does that get me to a place where the hydrogen is bonded to the carbonyl carbon? You could think of it as though hydrogen is leaving with its electrons from aluminum to make something like H minus and then just neutral AlH3. But H minus is a terrible, terrible, terrible leaving group, so that doesn't seem reasonable. So what's likely happening is it's a direct handoff of hydride from the aluminum to the carbon. The hydride never becomes H minus on its own per se, it's just directly handed off. All right? Is that okay? Anything you want to ask about that? Yeah?
Yeah, I just not quite understanding that, so I don't know if there's another way that we can put that.
Alternatively, let me show you what the transition state for this reaction might look like. I'm using the double dagger here to indicate that what I'm going to draw you is a transition state. In the transition state, the carbon-oxygen bond, pi bond, is breaking. There's some buildup of negative charge out on that oxygen. In the transition state, I'm starting to form a new carbon-hydrogen bond at the same time as I'm breaking an aluminum hydrogen bond. Yep. So never do I have H minus sort of on its own. Yeah. Yeah.
So kind of a two-parter. So you're saying instead of thinking of the hydrogen as a leaving group, think of that whole aluminum compound as a giving group?
Yep, as a donating group. Hydride donation.
And then what is the rate of this reaction?
What's the rate of the reaction? It's pretty fast. Yeah. Because of the large electronegativity difference between aluminum and hydrogen, lithium aluminum hydride, or LAH or La, is very reactive. You don't want it to be exposed to water or protic solvents, because if this hydride reagent is exposed to water, what happens is the very fast and rapid acid-base reaction, whereby hydride removes a proton from water, you end up making hydrogen, and if you do this in an uncontrolled and exothermic fashion, you can start a fire. So you have to use, for lithium aluminum hydride, you have to use non-protic solvents, and we won't necessarily worry about specifying those, but you have to be careful with this reagent. It's highly reactive, and we're going to come back to that a little bit later as a way to remember the kind of things that lithium aluminum hydride does that other reagents don't do. A second reducing agent that your book mentions is sodium borohydride. Same deal, boron and hydrogen. Boron's more electronegative. I get it wrong every time. Boron's less electronegative than hydrogen, so BH4 minus can similarly deliver a hydride to a carbonyl compound via exactly the same mechanism. Now, what I showed you after that first step is that we make a tetrahedral intermediate. So in the reaction one, we've got here the aldehyde with aluminum hydride, here the ketone with borohydride. We can use these two reagents interchangeably for these starting materials. Look at this tetrahedral intermediate. Does it have any good leaving groups on it? No, it's just got hydrogens and carbons, and negatively charged hydrogens and carbons are generally very bad leaving groups. So we're stuck until after the reaction's done. Then then we add water, and water protonates the negatively charged oxygen, and we end up with our alcohol. Someone during the first hour, I teach the same class at 9, asked, well, wait a minute, you just said you don't want lithium aluminum hydride to touch water. And that's true if you want lithium aluminum hydride to do the reduction reaction. once the reduction reaction's over, you can add water in a controlled way at cold temperature, and what that does is it quenches the remaining aluminum hydride reagent and it protonates your alcohol. With sodium borohydride, it's less reactive than lithium aluminum hydride. So this is not something that we necessarily are going to explain, but you can use protic solvents. That's a minor detail, but for aldehydes and ketones, you can use these reagents interchangeably. Sometimes when I am in a hurry, I won't show the second step of this reaction where suppose we're using sodium borohydride as the reagent, we can use methanol as a solvent. Likely, as soon as that tetrahedral intermediate forms, it gets protonated by methanol to give you your alcohol. Okay. So notice that everything so far is following the pattern that we've learned last time. Nucleophile attacks the carbonyl carbon, you get a tetrahedral intermediate. What happens next depends on if there's a leaving group or not. So if you understand these reagents and what they do, that is, they are hydride delivery reagents, you don't need to memorize that aldehydes react with lithium aluminum hydride to give you primary alcohols, because that consequence follows naturally and automatically from your understanding of aldehydes and the reagent. Similarly, you don't need to memorize that ketones react with sodium borohydride or with lithium aluminum hydride to give you secondary alcohols, which is what this is, because that's just a natural consequence of the reactivity of a ketone and the hydride delivery reagent. All right. Anything you want to ask about that? Yes?
So after you react the NH4, normally I would say take off a hydrogen, the charge is one less positive. Is that reversed here, or what's the other product?
Oh, okay. After the hydride, it's a great question. The question is, after the hydride is delivered, what's left behind? It's a great question. We typically ignore it, but I'm glad you asked, because this sort of helps explain why aluminum hydride and borohydride can deliver the hydride in the first place. That's because after they deliver H-, they're now only bonded to three things. They're now neutral. BH3 is borane. You encountered that in 351. Aluminum, I don't even know what this is called actually. AlH3, also neutral. We're not going to worry about what happens to these. Okay. Good. Others? All right, so we need to talk about stereochemistry, because I deliberately chose a ketone where there's no stereochemical issues in the product, but imagine if we had started instead. pH is the abbreviation for a benzene ring. I will do that when I am lazy, which is much of the time. So let's show you what would happen if we add lithium aluminum hydride, and then afterwards we add water to protonate the tetrahedral intermediate and to quench the LAH reagent. We're going to deliver a hydride to the carbonyl carbon, and then the oxygen is going to get protonated by water. That gives us this alcohol. Now notice that we have an sp3 hybridized carbon that's attached to four different things. We just made a stereocenter. And there's no chirality out of nothing. There's no ex nihilo chirality. So what that means is if you have a non-chiral starting material and non-chiral reagents, but you make a stereocenter, you have to make both configurations. All right? So let me show you how that happens and how you might communicate that. remember that the carbonyl is flat, sp2 hybridized trigonal planar. So the hydride delivery reagent can deliver from above or below the plane of the page. But from your perspective, from in front of the screen or behind the screen, because the carbon oxygen pi bond, because the carbonyl is laying in the plane of the screen, as I'm showing you. So that can happen from above or below. If the hydride is delivered from above, we get this stereoisomer. If the hydride is delivered from below, we get this stereoisomer. And you could, I don't really like the wedge that I drew there, you can go through and figure out which one is R and which one is S. That's not necessarily important for what we're talking about here. But the question is, how do you communicate that when you're solving a problem? So the most unambiguous way is simply to draw both enantiomers, okay? A related way is to simply draw one of the enantiomers and then include in parentheses a plus and a minus. That plus and minus it derives from the fact that chiral compounds rotate plane polarized light either in a clockwise or a counterclockwise direction. If one enantiomer goes clockwise, the other's counterclockwise. So the plus and the minus indicate you've got both. That's old nomenclature, but you can use it if you want to. The alternative is actually just to do what I've done here, and that is to not show any dashes or wedges at all. Without any dashes or wedges, you can't tell whether it's R or S, and that communicates that you must therefore have both. Okay? So that blew people's mind in the first hour. There was this muttering among the crowd about, and I asked them if I had committed blasphemy or something, and I think the response was that they were just surprised that we could be that lazy. And I'm like, yes, you can. But be careful. But before I answer that, I got a hand over here.
Yeah, I was just going to ask, like, last semester probably would have gotten like 50% on exam for doing that. So, like,
yeah.
On an exam, we're allowed to just write without any dashes or wedges, and you'll consider that as...
Only if you mean, if you draw this, I will interpret it as this.
Okay.
Yeah. Now, not using dashes or wedges can cause you problems. Let me give you an example. Suppose, I sort of made this up last hour, but suppose that you want to do the reduction of this ketone. We're using sodium borohydride. That's going to reduce the ketone to the alcohol. And then suppose you did this. Okay. That was too lazy, right? This is a chiral starting material. This has a stereocenter there. It has a specific configuration. Moreover, this reaction doesn't mess with that carbon. It only attacks the carbonyl oxygen. So there's no way that this reaction would change stereochemistry here. But if you draw this, you're telling me that you think that happened. Now, probably you don't think that happened, but you were too lazy in how you communicated, and I will hold you responsible for that. So what I'm saying is, if you wanted to do this, you would still, if you have a specific stereochemical configuration at a carbon and it's not involved in the reaction, it's got to stay the same. Okay? Laziness, but principled laziness is what we're looking for. Okay? All right. Any questions about that? Now, nature, being chiral, can do reduction reactions that favor one enantiomer over the other. we'll talk about this. But first, we need to introduce the fact that nature doesn't use aluminum hydride or borohydride as a reducing reagent. Aluminum hydride's obvious because you don't want to use a reducing agent that starts fires in people. Borohydride, you can use protic solvent. I'm not sure why nature hasn't chosen to use boron. It may have to do with toxicity or something. But I'm going to introduce nature's reducing reagent of choice. This is called nicotinamide adenine dinucleotide. And if you know stuff about biomacromolecules, that name makes sense. If you don't, it's a bunch of gibberish and we'll explain it, but this is often abbreviated as NADH. So yeah, same thing happened last hour. There's a little bit of, oh. Some of you have heard of that before in what, cell bio or something? Okay. So let's actually talk about what on earth that is. Nicotinamide stands for this portion of the molecule. It's a 6-membered ring with a nitrogen. Oops, there are double bonds here. There are 2 hydrogens here. This carbon is sp3 hybridized. I'm using dashes and wedges there not because it's a stereocenter, because it's not. I just want to communicate the tetrahedral geometry of that carbon. Then it has this branching sort of side chain group. So that's the nicotinamide part, and that actually is the business end of this molecule. And if we're drawing a mechanism, that's really the only part that we're going to need. Just as an aside, you get this portion of the molecule from the vitamin niacin, which is vitamin B3. And so when you open up your bag of marshmallow mateys in the morning and you're reading the back because you're bored and your phone's out of charge, and you see that it contains X percent of your daily value of niacin, that means it's been fortified with this stuff. All right, so what's the rest? Well, this nitrogen is attached to a 5-membered ring sugar called ribose with oxygens here. Then there's phosphates here. This is where the nucleotide part comes in. You've got a phosphoanhydride linkage here. And then, the other part of the molecule is here, another 5-membered ring sugar. And then we're going to put the base adenine at this position. Now, while we're having so much fun drawing, let's deal with the question of, do we have to memorize that structure? Of course not. That would be silly. But I want you to understand how it works. And I want you to understand, in particular, this portion of the molecule. All of this stuff is really for the enzyme to hold on to. The reactions happen here. All right, so let's talk about how this is a hydride delivery reagent. Any questions you want to ask about this, though? I'll let you in on a little secret. My exams are multiple choice generally, so you're not really going to be drawing anything from memory. You may think that's good. You may be relieved. You shouldn't necessarily be. The averages on my multiple choice exams are about the same as my free response exams. You can bet that if this were a question on an exam, among the many options that might distract you from the correct answer would be one that gets the stereochemistry wrong. So, but anyway, memorization is not of structures is not necessarily a worry that you need to have. All right, so how does this work? I'm going to show you a specific reaction that nature does. I'm drawing here for you the alpha keto acid pyruvate. This is the endpoint of glycolysis. Under aerobic conditions, pyruvate gets shunted to the citric acid cycle, where you can get more equivalents of ATP out, but under anaerobic conditions, it can accumulate. And when that happens, there's an enzyme that reduces pyruvate to an alcohol form, and that enzyme uses NADH. During the first hour, there were some people confused about why I had shown the carboxylic acid here in its conjugate base form. That's simply because at pH 7, that's the form that exists. Carboxylic acids have a pK of around 4. At physiological pH, that proton is gone. If that's unfamiliar to you, you learned it probably in chapter 2, but we're going to review it again in a couple of chapters. It has to do with something called the Henderson-Hasselbalch equation, which you may remember with fear and trepidation from Gen Chem. It's not that bad, and we're not going to use it in the way that you think. We're not going to calculate buffer pHs. Okay, so another question I got during the first hour is why we're going to show the reduction reaction happening here at the ketone. And people asked, why not at the carboxylic acid? Well, once it's negatively charged, the carboxylic acid isn't reactive. That negative charge is going to repel nucleophiles. So we're going to show a hydride being delivered from NADH. We're going to show a hydrogen with its electrons being delivered from NADH to the pi star of the carbon-oxygen pi bond, thereby breaking that bond with electrons moving out onto the oxygen. Okay, so what we just did is analogous to what we did above with hydride delivery reagents. We take an arrow, we start with a bond between hydrogen and something else. We take those electrons, we move them to become a bond between hydrogen and the carbon. And then we break the pi bond. So, as before, you may be worried about why are we showing H- leave as a leaving group? The answer is it's a direct handoff. If you go look at X-ray crystallography structures of enzymes that do this reaction, they put that part of NADH right immediately next to the carbonyl, and so it's a direct handoff like we talked about before. Now, let's draw what you get as products. Oops. You're going to get, I'm going to make sure I get the stereochemistry right. The enzyme blocks one face of the ketone such that the hydride is delivered, in this case, from above. You would get a tetrahedral intermediate, which is going to be protonated by water. I'm going to skip showing that step because I'm lazy. But understand that you'd form the negatively charged oxygen first, and then you would protonate that oxygen using water or some other acid. The molecule we form is now called lactate. And this is associated with the feeling of tired muscles you get, especially if you've done a lot of sort of anaerobic activity. What happens to NADH? Well, let's look at what's left. In fact, let's just draw only the nicotinamide portion because that's the only portion that will have changed. So we'll use an R group here. Now, we used to have this carbon bonded to 4 things, but we took away hydrogen and its electrons. So now we only have 3 things. So what needs to be left behind on that ring? A plus charge, right? That's what would be present if you imagined a leaving group leaving with its electrons. There's a positive charge left there. And this is called NAD+, but it's not usually drawn in this form because there's a better resonance structure. You can take lone pair electrons on that nitrogen and move them as shown here to give you the following structure with the positive charge on the nitrogen, but everything has a full octet, and so that's why that's a better resonance structure. In any case, this provides some explanation for why the hydride is able to leave in the first place. Because once it's gone, you restore conjugation to that six-membered ring. Notice that before in that six-membered ring, you've got some conjugation here between lone pairs and pi bonds, but you have an sp3 hybridized carbon there that can't participate. Once that hydride leaves or is delivered to the ketone, now you have a fully conjugated six-membered ring. You learned about conjugation, those of you that took 351 last semester, you learned about dienes and conjugation, yeah? So you know that that's a favorable thing. We haven't learned about something called aromaticity yet. That refers to conjugation in a ring of the right size with the right number of electrons. More to follow, but I will just say that NAD plus is aromatic, and you get an even better stabilization from that than you get from conjugation alone. And so that effect pays for losing the H minus. That's why it's thermodynamically favorable for NADH to deliver the H minus. Okay, so that's how biology will do reduction reactions. Questions you want to ask about that? Go ahead.
Pyruvate reactions, why does the hydride break up that pi bond?
Why does the hydride break up the pi bond instead of
Instead of the other one?
Instead of this one? Yeah? Instead of this one? Yeah. The reason is, remember, you're attacking the anti-bonding orbital between the carbon of the carbon-oxygen pi bond, and mostly that's at this carbon. There is an anti-bonding pi star here as well, but it's higher in energy because of the presence of this negative charge. The other way of thinking about it is the negatively charged carboxylate repels a nucleophile. So this site is more reactive than that one. This site is electron rich. This is electron poor. Yeah, others, go ahead. If this were done under acidic conditions, would it still attack? That's hard to say in the sense that you probably couldn't change the pH without changing enzyme function, so I'm not even sure how to answer that question. That being said, later on we're going to see that there are reagents that are selective for ketones and aldehydes versus carboxylic acids and esters. Sodium borohydride actually will reduce ketones in the presence of acids and esters for reasons that I don't really understand. Yeah, go ahead.
And we should just assume that the negatively charged oxygen on the pyruvate doesn't just pull the hydrogen off of the NADH somewhere?
You should assume that this negatively charged, this negatively charged oxygen is different from the negatively charged oxygen that's present in the tetrahedral intermediate. This one is resonance stabilized, this one is not. The pKa of the conjugate acid of this one is 16, the pKa of the conjugate acid of this one is like 4. So the negatively charged carboxylate is more stable and happier in aqueous solution than this negatively charged oxygen is. Good. What else? Yeah.
So is the top position of the hydride just due to the enzyme?
Yeah, is the fact that the hydride gets delivered from the top just due to the enzyme? Yeah, and we can do a really sort of hand-wavy thought experiment. Matt, your hands are chiral, right? People are chiral. Your right hand is the mirror image of your left hand. Imagine one of your hands sort of being the enzyme and sort of holding pyruvate from underneath. That blocks the bottom face of pyruvate, but the top face is available for attack. What happens is the enzyme holds the pyruvate and the NADH in a specific orientation such that that's the only option. Another question that happened during the first hour was I showed this hydrogen that's up being delivered instead of the bottom one. Does that matter? There's evidence that it does, but we're not going to worry about it. Okay. Just a little bit of maybe background as to some things you will see later on in biochemistry. Biochemists will sometimes draw this reaction as follows. They'll draw pyruvate, and then they will show that going to lactate. And then they will show NADH here. And then they will usually put a comma and a proton, and then a curvy arrow here to indicate that the enzyme takes NADH and converts pyruvate to lactate, and then what's left behind is NAD+. What the heck with the proton? Biology, I mean, there are, in biological context, in aqueous solution, there's no such thing as a H+ on its own. It's always like H3O+, right? What do they mean by that? That's just shorthand from recalling the fact that first, when you reduce the pyruvate, you have a negatively charged oxygen tetrahedral intermediate, which then in the next step gets protonated by water or something else to give you lactate. And notice before I told you that was happening in words, and I just drew the arrow, and I said we were lazy and we were okay with that. I guess biochemists have a different standard of what principled laziness is, and they're wanting to make sure they balance their equations. So if you ever see NADH, realize that this is the H on NADH is the hydride that gets delivered as the nucleophile. And then this proton is the one that goes on the negatively charged oxygen. Another thing is that sometimes these enzymes are named for the reverse reaction. So you can use, just as you can use NADH to convert pyruvate into lactate, you can take lactate and NAD plus and go the other direction. And so this enzyme is called lactate dehydrogenase. That's not anything worth memorizing, but when you see an enzyme called a dehydrogenase, it almost always involves an oxidation or a reduction reaction using NAD plus or NADH. Notice if you compare lactate to pyruvate, what's the difference? You've lost this hydrogen and this one. So the dehydrogenase is the thing that does that. So anyway, these are just some sort of previews of what you will encounter. And this kind of reaction happens all over the place in metabolism, and we'll come back to that many times. Anything else you want to ask about that? Dang, that was probably too long on the biology. Oh well. All right, let's now talk about what happens when you react some of these reducing reagents with a carbonyl compound that's got a leaving group on it. We'll use Z here, where Z equals like Cl or maybe OR as in an ester. We'll have some others in a little bit. Let's start with the acid chloride, and let's have lithium aluminum hydride react with the acid chloride. We're going to do exactly what we did above. Aluminum hydride is going to deliver H- by direct handoff to the carbonyl carbon. We will break the pi bond. We will get the familiar tetrahedral intermediate. Only this time, unlike before with the aldehyde and the ketone, we have ourselves a good leaving group. And it's favorable for the negatively charged oxygen to kick off Cl-. And the reason you can tell that's favorable is because a negatively charged chlorine is more stable than a negatively charged oxygen. The way you can tell that is because the conjugate acid of negatively charged oxygen is an alcohol with pKa 16, whereas the conjugate acid of chloride is HCl, pKa -9. I'm just trying to say that this forward reaction is very thermodynamically favorable. So we lose the chloride, but now we're in a situation where we've made something that we already know can react with lithium aluminum hydride. Okay? So we've got a conundrum here because we know that this next step that I'm going to show you is perfectly reasonable for aluminum hydride to deliver another hydride to the aldehyde, and that will make this tetrahedral intermediate, which, if in a second step we added water, we would protonate on the oxygen to get the alcohol. Okay, so at this stage, some students ask, why can't I just add 1 mole of lithium aluminum hydride for every mole of acid chloride and just stop at the aldehyde? Doesn't that seem simple? The reason why that doesn't work is a little complicated. I'll try to give you a sense for that, but if you want to just memorize that lithium aluminum hydride cannot stop at the aldehyde, that's perfectly fine. And if you want to remember that that's because lithium aluminum hydride is so reactive, that's good. 2 reasons. First, as soon as you form some aldehyde at the very start of the reaction, the aluminum hydride reagent that's left has to choose between reducing acid chloride or or rather the aldehyde. So if you only added 1 equivalent, presumably you're going to get a mixture of products. You're going to get a mixture of the alcohol and the aldehyde. The second and probably better reason is that the aluminum hydride reagent actually can deliver, each mole of aluminum hydride reagent can deliver 4 moles of hydride. That's through some details that we don't need to worry about. Okay, so LAH, lithium aluminum hydride, cannot stop at the aldehyde. It goes on to the alcohol. We're going to talk probably next time about reagents that can stop at the alcohol. But this will happen with esters as well. So if I use lithium aluminum hydride, now I'm getting really lazy. I will also reduce the ester all the way to the alcohol via the same kind of mechanism, which I won't draw for you other than to show you the tetrahedral intermediate where the hydride has been delivered. The negatively charged oxygen here is perfectly fine, kicking off another negatively charged oxygen. This is about as stable as that, so this forward reaction is favorable. You make the aldehyde, and again, you can't stop, and you go on to the alcohol. All right? So, lithium aluminum hydride is reactive enough that if you start with an ester or an acid chloride, it's going to go all the way to the alcohol. All right. We need to say one thing about sodium borohydride. Sodium borohydride is selective for ketones and aldehydes, even in the presence of esters. So here is an ester. ET stands for an ethyl group. Hopefully that's okay. If I use sodium borohydride, and I'm just showing the solvent for completeness, though I wouldn't expect you to worry about that, we can reduce the ketone to the alcohol without touching the ester. In contrast, if we expose the same molecule to LAH, we're going to reduce both the ketone and the ester to the alcohols. So on top is the sort of selective finesse approach. On the bottom, you're bringing the hammer. Now, somebody pointed out after class during the first hour, they said, you told us that sodium borohydride is less reactive than lithium aluminum hydride. And then you said lithium aluminum hydride is so reactive that it can't stop at the aldehyde. But then how does that jive with the fact that sodium borohydride will react with aldehydes but not with esters? And I think you have to conclude that esters and acid chlorides are a little bit more electrophilic than aldehydes. I'm sorry, I'm going to mess this up. But do you see the problem, right? We've said that lithium aluminum hydride is so reactive it can react with esters and then won't stop at the aldehyde. Sodium borohydride is less reactive than that. So why can't it stop at the aldehyde? The answer is the aldehyde is more reactive than the ester starting material, right? So it's not quite that lithium aluminum hydride can't stop at the aldehyde. It's that lithium aluminum hydride can react with the ester, whereas sodium borohydride can't. Okay. Let's see. Questions? Yeah. Yeah, I mean, this is something that we don't need to spend a huge amount of time on. I didn't actually tell the first class this, but because we'll have a chance to talk about these issues in the future. But if you compare the aldehyde with the ester has a resonance structure that looks like this. Lone pair electrons on that oxygen can donate into the carbonyl carbon, and that makes it less electron poor. In an aldehyde, you just have a hydrogen. There's no resonance stabilization there. So from some perspectives, the aldehyde is more reactive than the ester. Other questions? Yes? Is this alcohol because of? Is that because of tautomerization? No, that's an issue we'll talk about later, but that's because we made an ester. Okay, give me just a second so that I can answer the question. We make the ester, it gets reduced, it gets converted to the aldehyde, and then we react with the aldehyde again to give you the alcohol. Yes? Yeah, so the question is about methanol as a solvent instead of water. Probably that just is a practical consideration, solubility of the starting material and so on. Okay, my sense is that we're probably a little bit behind relative to the schedule. Probably it's not till Monday that we finish up chapter 13. Of course, that's not going to affect when you have to put the study guide stuff information in. So I will see you on Friday. Have a good day.